Hey everyone, short video I promise. Let's talk about the enthalpy of solution for ionic compounds. What I have here is an illustration of something called calcium chloride. Um, this particular compound is held together by electrostatic forces of oppositely charged ions. We're going to think of the enthalpy of the solution as happening in three distinct phases. Step one is the lattice energy that holds these ions together must be overcome by a polar molecule like water. Now, lattice energy can vary depending on the type of compound you're discussing. In the case of calcium chloride, yeah, calcium has a larger atomic radius than some metals, but it happens to lose two electrons, and so it loses its entire 4s orbital. So its ionic radius does get a little bit smaller. And what also keeps the uh, lattice energy of calcium chloride reasonably high is the fact that calcium has a 2 plus charge here, requiring two additional chloride ions to neutralize overall charge. Coulomb's law is a central theme here, which states that the overall attractive force is determined by the radius or difference in distance here, and also the charge value. Second thing that's got to happen is that the intermolecular forces of water have to be overcome. This is also, both these processes here are endothermic because they're going to require breaking of bonds or attractive forces. Now, this is going to be less endothermic than the lattice energy because London dispersion and dipole-dipole forces are far weaker than lattice energy or electrostatic forces. Third step is what we have in terms of hydration cells, as they're referred to in the textbook. Sometimes they're called enthalpy of hydration, but basically this is called solvation. And what happens here is that we have a new force that's being created where the ion that was being held by electrostatic forces here is now surrounded by a polar water molecule. And the ion dipole force is actually going to be stronger than the hydrogen bonding force because we have a formally charged species that is going to reorient water molecules based on its polarity. And so the formation of these new forces, you can see how there is quite a lot of water molecules that are required to surround these ions. This is going to be an exothermic process overall because I'm creating new attractive forces. What's going to really determine if your enthalpy is endo or exothermic is the type of compound you're really discussing. Here's another image of some other ionic compounds in the same three-step manner. I've got sodium bromide versus magnesium oxide. Now, I would suspect magnesium oxide would have a much higher lattice energy because the overall ionic radii of the species involved here is going to be far less large than the sodium bromide. And so the attractive species here are going to be harder to overcome. So this is the equation that helps you determine the enthalpy of solution because these steps are sometimes hard to measure, and we can rearrange the equation and think of it this way to help determine if this is going to be an endo or exothermic process. Mostly because we know lattice energies of a lot of different ionic compounds, and we also know the value of the hydration of ions that can be measured because that's also usually put together in a nice table in most textbooks. So these three steps are going to be what determines the enthalpy of solution.